Boosting Ensembles Part 2. And these first two slides are going to be familiar because they're from the Part 1, just a little review. If they're not familiar to you, go watch Part 1. You didn't pay enough attention if any of this looks new on these slides. But just to remind you, we're doing Ensembles to help us have new tools to deal with the bias variance trade-off challenges that all models have. Simple models can't represent complex concepts because they will have bias. But if you use more complex models that don't have such strong biases, you will tend to have variance problems where you overreact to small changes in the data. But using ensembles, instead of building one model, you can learn several or many and combine them. Depending on how you combine them, you can either get rid of variance mistakes by averaging things out, or actually get rid of bias problems by having a bunch of models that each learn a small part of the concept that you're trying to learn and then combine them at the end. And often ensembles can give you significantly better accuracy. Last lecture, we talked about approach number 1, which was what? Bagging in random forest. Sometimes, boosting and bagging. Everyone says boosting, bagging. And then when I say it, sometimes I glitch and which one am I talking about, boosting or bagging? It's a good thing to know, right? Bagging was lecture 1, boosting is lecture 2. And we talked about random forest, and the idea here is to have high variance learners that can learn with relatively low bias and then combine them. It's robust against overfitting because of the way things average out problems. Simple to use. What we're going to talk about in this lecture is that act of learning different parts of the concept with different models and then combining. I didn't mean to cross that out, I meant to underline it. Models and combining. And this can work with high bias models or weak learners. Remember my story about weak learners, how I learned about weak learners. And it can also help deal with variance problems, but it may tend to overfit, so you have to do that training versus validation data and some criteria for stopping essentially it's called using a holdout set to determine when to stop training more and more models. We'll get into it. But first, we're going to go and look at a conceptual sample of why and how an ensemble could work. Now, if you remember last lecture, we talked about trying to learn a concept that looked like this, a linear model with decision trees that could learn structures like that. And now we flipped it. So now the concept is essentially a decision tree, and we're trying to learn it by averaging a bunch of linear models. Conceptually, it doesn't seem like that'd be too hard to do. I mean, you've learned one linear model, you go off and you learn a bunch more linear models off of bootstrap samples of the training data that is using this concept. The problem that you may or may not see here, but is that all of these guys learn the concept about the same way. I mean, they learn it a little bit differently, but really when you look at them, there's nobody trying to learn like a concept like that or a concept like that. They're all learning slight variations of this concept because that's the best that this high bias, low variance model can do with this concept. And so, there's always going to be a chunk there. There's always going to be a chunk there that none of the concepts really learn at all, and that you will never get correct using this approach of doing these models and averaging them. And just to prove it with one example, which doesn't prove anything, I did the averaging there and the accuracy of 92.7. You can look at the individual base models. 92.7 in this particular case was better than any of the base models. It did do a slightly better job of figuring out exactly which hyperplane to use to maximize things. Took out a tiny bit of variance, but it really wasn't able to overcome the fundamental bias problems. You could average 100 and it, in this case, it did worse. It could do better. Who knows? You could average 500, but you're really not getting to where you need to be. All you're doing is going further down a dead end path, which is going to learn you, pretty much a model that looks like that. Not ideal. Okay, so that's the reason that bagging is not sufficient to take a model with a high bias and low variance and turn it into an accurate representation of, pretty much any concept. Now let's go through a little conceptual run through of what boosting might be. And now this conceptual rundown is not exactly accurate for classification. This is more of a regression thought process. And we'll see over the next few slides how you would apply this to classification. But to get started, let's just say that Y is the regression task you're trying to do. X is your instant. F is the concept we're trying to learn. So f of x is some number. Let's say it's the house price. Let's say, you put in the properties of a house and the price comes out at like $150,000, something along those lines. Fine. So then you get a bunch of houses where you have the properties of the house and the price. It's a training set, just like whatever. So we got to click so we can get that to come up. And then you build your model. And in this case, H1 is the hypothesis that you've got from training off of this appropriately used training data where you split it into validation and do everything you're supposed to do. But H1 is the hypothesis or the first model that you've learned. And Y hat is the prediction of that first hypothesis on a particular sample. So this was supposed to be 150,000. Who deleted the one? It was probably me. So let's say Y hat for this house is $125,000. Well, now you have a problem because H has predicted it wrong. So what can you do? Well, one thing you could do is say, well, how wrong did H1 predict that particular sample? And here, Y minus H1's prediction is equal to the residual. In this case, the residual would be $25,000. And so you could say that the residual is the part of the concept F that H1 did not learn. Some houses, H1 will have perfectly correct. I mean, let's say it's possible that some houses H1 will have perfectly correct, in which case the residual would be 0. For a particular house, it's perfectly correct, 0. Some houses H1 will be totally morbidly confused. And if the purchase price was like 200,000, H1 might say it's $2 million. Totally wrong. And in this sense, the residual contains a number which is how wrong for that particular part of the concept was H1. What can you do with that? Well, you could make a new training set. And this new training set has everything exactly like the original training set, except instead of trying to predict the Y labels of the original problem, you now try to predict the residuals of H1. So you take your original Y and subtract off what your first model predicted for the X. See, X is in both places there. And now this gives you a new training set. So you can tell the second model, H1 went and did something. Who cares what it did? Here's the problem that's left over. Here's what I still need to solve. Here's the residual. Let's go learn an H2 to try to predict that residual. And if you were going to use these models to make a prediction at runtime, you could do something like that, where you take both of your hypotheses. This is your first shot at it, and this is the one that was trying to learn the residuals. And when you add them together, H2 has an opportunity to correct the mistakes that H1 made, and you presumably will end up with a better Y hat than H1 could get to alone. Because now you have a second model trying to learn the parts of the concept that the first model was unable to get to. Now you could keep going. I did 2 here. You could do K, just like we were talking about in the bagging case. You could do as many as you want, as long as you look out for overfitting. Because let's say H1 learned every house correctly except for the 5,000 that had crazy noise or corrupted data. Then you could learn a whole series of models trying to predict that corrupted data, and that's not going to help you. That's just going to make you overfit. So, other than this criteria that you might not want to just blindly pick a K, but you might want to have some overfitting correction as a hyperparameter in the search process, this is essentially what we're talking about when we say boosting. All right, now let's go through another way of looking at this a little bit more mechanically, because remember, you are going to have to implement this. So now we're going to start talking about how to relate the residuals we talked about on the last slide with what do we put into our models here where we're trying to do classification. And the answer to that is going to be sample weighting. Now I'm going to breeze over it on this slide. On the next slide, I'm going to go through it in more detail. But essentially what this means is that we apply to each sample a weight, which tells the learning algorithm, this is how important this sample is for you to try to get right. It essentially takes the loss from that sample and multiplies it by the weight. So if a particular sample had a weight of 0, then you would be telling the learning algorithm, don't worry about this sample. Pay no attention to it. It does not contribute to your loss. if you gave a sample a weight of 2, that would be like this sample counts as double when you're calculating the loss. So it's twice as important to get this one right as it is to get right any other single sample in the data set. So that's just a little primer on sample weighting, but we'll get into a little bit more detail in a second. But for now, the way you would think about boosting is you would start with your training set and you'd split it up into train, validation, test, all the stuff that you would normally do. And you'd learn a model on the training data. Now, in this case, we're doing a linear model. It's not, a super weak model, but it does have high bias, particularly for this problem we're talking about. It's not going to learn it very well. The next thing we do is we go and we reweight the training set. Now, reweighting means that for every sample that this first model gets right, we lower the weight. And we say, we have a new training set here that says that all of these samples in this region up here that we got right, they're less important. Downweight them, cut their weight in half, cut it, whatever. We'll see the algorithm, the math of how you're going to cut it, but downweight it. And then for every sample that the model got wrong, which would be like in these regions here, we're going to either leave the weight the same or upweight the weight. I mean, essentially, you want to say stuff that's right, less important, stuff that was wrong, more important. Learn a new model with those sample weights. And that might be what you get, something like that, la-di-da. Then you do it again. And now you're reweighting based on things that have been kind of consistently wrong in this entire process. And in this particular little example, you can see that now we're starting to get to the point where we're getting in on those, hard regions of the little concept that we've been talking about. You could keep going, reweight it again, do it as much as you want. And then at the end, you do an ensemble prediction by voting. But each model in the boosting case gets a vote based on its accuracy. So things that are more accurate, the vote is controlled by how much that model is contributing to the overall accuracy on the entire set. And in this particular example, you can see it's starting to get a little bit of a curve there. It's much better than those straight things we were seeing before. And we're heading in the right direction. And you'll see in the assignments how far you can get using this approach. All right. So to say all the words one more time, each model trains on the mistakes or residuals from the previous runs. And it does this by upweighting samples that previous runs were getting wrong and downweighting samples that previous runs were getting right. Models must be trained in sequence because in order to know how to reweight the samples there, you have to know what mistakes that model was making. In order to reweight there, you have to know the mistakes that guy was making, and et cetera, et cetera, et cetera. So that's a little bit of a disadvantage at training time. You can't get this obvious parallelism you could get with bagging or random forests. Later models are targeting samples that everyone got wrong. And so this could be samples that are just plain noise. There's no way to get them right because they don't make any sense. They're not related to the true concept. They could be samples that have corruption. They could be samples that are just really hard and maybe not so important, like really special cases. And in that sense, you have to worry about overfitting. But a simple run through of this is conceptual boosting is you learn the base model, reweight the training samples so mistakes get more focus, learn another base model, stop when you're starting to overfit. That is, if you use a holdout set like the validation data to figure out what the parameter for the number of base models to learn is, you would sweep that parameter up until you start to see the training loss and the validation loss diverge. And then you might say, oh, that looks like where we're starting to overfit, let's stop. And then the final answer is a weighted vote of all the models. Now we have something new to add to our learning algorithms. And this is one of the reasons that last year I had everybody just implement bagging, because now you have to go into the guts of this decision tree program that you already just wrote, that you already just debugged, and you're going to have to add sample weighting into the guts there. But essentially with sample weighting, each training example now goes from being a feature vector and a label to being a feature vector, a label, and a weight. So each sample will have a number next to it, which is like 0 if you shouldn't pay any attention to it. And it can go up as far as you want. The boosting algorithm constrains everything to be in the range of 0 to 1, but that's not necessarily necessary. Okay, now how are we going to use these weights? I'll tell you. For logistic regression, remember, we calculated the gradient by taking the derivative of the loss function with respect to the parameters, and we came up with something like this. So it would say you sum over each training sample, and you take the amount of wrongness it had times the feature that you're trying to find the gradient for and sum that up, and that would be the direction of the gradient for feature J. Now, if you were doing a weighted version of that, all you need to do is insert the weight for the sample here. So, you know, if it's a 2, you would essentially double the gradient from that sample. If it's a 0.5, you would essentially cut it in half. And then you would use this to calculate the sum of the total gradient. So that's pretty simple to do. Just put the weight in there and you're on your way. But we're not going to do boosting with logistic regression. We're going to do boosting with trees. So remember, for trees, the loss we were using to decide which feature gave us the most information gain was defined roughly as this. For each sample, filter it to a leaf and calculate the entropy at that leaf and sum that up. Well, very similar trick. We just take that and we multiply for each sample. It contributes an amount of loss proportional to its weight. But it's a little bit more complicated than that, because if you remember, the entropy calculation includes this information about the samples that filtered into the leaf. And so you'd want to apply the weighting there as well. So go from the percent of, P log P, the percent of samples with class label equal to I. So you go from the percent of samples with class label equal to I to the percent of the sample weight at that leaf with class label I. I think you can work that out from there. If you have questions, show up at office hours and we can work through that in some more detail. But that's what you're going to need to do. You're going to need to add a weight parallel to your training data. You're going to need to manage filtering it down the trees when you're making recursive calls and splitting the weight appropriately, the same way you had to split these other arrays. You're going to have to update your loss function and your information gain calculation to sample weight the entropy. And then at the leaf, you're going to have to change the way you calculate the entropy to be sensitive to not the percent of samples at the leaf that have a particular label, but the percent of the sample weight mass at the leaf that has a particular label. Now we'll go into the details. Let's go. Adaboost. Adaboost takes S, which is the training set of samples, just like you're used to with a classification task. Each yi is in a set. For us, we're going to do binary classification. This is with the adult census data set. So that's, over the dollar amount, under the dollar amount binary. Learn, the parameter learn is a learner that is capable of taking in training samples, but also a parallel array of weights. So in essence, Adaboost can work with any learner. You don't need to make your implementation so flexible. Just make it work with decision trees or whatever the assignment says. And then Adaboost takes K, or a number of rounds. And again, that is a hyperparameter you can tune, or you can pass in a validation set and say, continue learning additional rounds until you converge on validation set, or the validation error the validation loss stops going down, something along those lines. But for the simple version of the algorithm, K is just a hyperparameter that you tune externally. Now, in the first step of this algorithm, we take all the samples and give them a uniform weight. And that's what this says. For all I in the training samples, the weight in the first round for sample I is 1 over M, where M comes from up there, and M is the number of samples in your training set. Starting with uniform weight. Next step, R is the round number then you're in. So R equals 1 when you start, round number 1, and K is the number of models you want to build, or the number of rounds you want to do. We just discussed that. Now I skipped over a line here. That is we're gonna talk about that at the end. It's essentially on the first round, it does nothing because you've already done this, so it'll be a no-op. Trust me, you'll see. So skipping that, the next step is you learn the model using the weightings that you have at this round where they're all uniform. So learn on the samples with the weightings, and you have your hypothesis for round R, in this case H1. The next step you want to do is compute the error. That is, how good is H1 at the concept we're trying to learn? And this is a great way to say it. It is the sample weight of incorrect training samples. And the way you calculate that is you sum over all the training samples and you take the weight of that sample in the current round, is what that says, and multiply it by 1 if hypothesis is not correct. So everywhere that the hypothesis you learn in that round is incorrect, not right, you multiply it by 1 times the weight of that sample in that round. And that is a little bit of a mathy way to say it's the weight of the incorrect training samples, sum up the weight of everything that it got wrong. Now, if that weight is greater than 50%, if the hypothesis you just learned gets more than half of the weight wrong, then you're in a sort of pathological case and you might as well just stop. Right? It's a really bad sign. That's like a crash case and you better drop out. If not, you calculate this beta, which you're going to use for the round. And the beta is just related to the amount of sample mass you get wrong. And I plotted it up here. It scales between 0 and 0.5, which was the crash out case. And it scales beta from 0 up to 1 with that little bit of a curve. Just a convenient thing to do. I'm sure there's some deep theoretical reason behind why that's chosen about how you're dealing with the sample mass and blah. We're not going to go through that. The next step to do is you have to reweight the samples. So this is the line here that takes all the errors that model made and updates the weights of the samples so that the next learner will focus on the things it's supposed to focus on, the things that you had trouble getting right at this round. And the way you do that is for all samples, the weight of that sample in the next round, in the future round, is equal to the weight of that sample in the current round times beta to blah, blah, blah. And what does beta to blah, blah, blah mean? Notice the 1 minus this right here. So what that translates to is that if you are wrong, you get beta to the 0, which is equal to 1. In that case, you keep the sample weight the same from the previous round. So every sample that the HR got wrong, you keep its weight exactly the same. And every sample that it got right, you downweight the weight from the current round by beta. And remember, if your error is small, your beta is small. So if this model is very, very correct, then everything that it gets correct is heavily downweighted. If this model is not so correct, then maybe it's not going to be such a good thing to use. Maybe you don't want to give it too many votes and you don't want to downweight the samples too much because maybe the next model will do a better job. And then the loop goes around, and this is the row we skipped, the line we skipped the first time around. And essentially what it does is it sums up all the probability mass, all the sample mass of every sample in the new round that you're in. And then for each sample, it divides its weight by the sum of everybody's weight. And what that does is normalize it so that the weights sum up to 1. So after this row, the PRs will sum up to 1. And when you call the learning algorithm, the weight of all the training examples it's going to look at will sum up to 1. That's essentially what that does to keep things well behaved. Then at the end, what you do is you have to vote the models. And the beta determines how much vote each model gets. The output, the final prediction of the model that you've learned with this, your hypothesis is essentially equal to the argmax over all the possible class labels. We're just doing binary classification, so we only have 2. You sum over every model, and if that model says the sample's value is yi, you sum it up and you give it a vote weight of log 1 over BR. So when the model makes a prediction for a particular class, that model votes with its beta, the beta that was during the round it was learned. You sum that up over all the different models and you take the class with the highest mass of the weight. Now, right here, I've plotted out the relationship between the beta on the round and this property log over 1 blah blah beta. And the beta, remember, is lower. If you go back up to here and remember, the beta is lower when the model has less error. So if there's less error, you would want to give it more votes. And that's exactly what you see here. As beta for the model's beta goes down, its vote weight goes up, to the point where if you're in this sort of pathological case where the error was very near this threshold where you were going to cut off, the model's getting essentially no votes, very, very close to no votes. That's the Adaboost algorithm. Now, what I want to do is one more look at this, which is stepping through a few rounds with some actual numbers so you can see what happens. And I guess I have to dip out of this screen as well. If your training sample is this right here, and all the class labels are 1, so it's not really something that you would want to predict. This isn't looking at the decision trees making the predictions. This is the mechanics of the boosting layer that we're going to talk about now. The first thing you would do is you would create the initial uniform weighting, and that is the combination of this line gets you uniformed weighting and this line renormalizes so that everything sums up to 1. And that's where you get the PRs, and R is equal to 1 because we're in the first round. So the P1s, sample weights for the first round, uniform, great. Now the next step is we're going to learn the model. H1, we've learned H1. Now the next step is we're going to see what the model predicts and add up its error. So if these are the predictions of the model, then the error is 0.25 because 3 of them are right, 1 of them is wrong, and the sample mass of the one that's wrong is 0.25. Then we just do a little bit of math, which is over here on the right, we calculate the beta right there, and the beta comes out to 0.33. Okay, now the next step is to do the reweighting. So let's take that step. And weight for round 2 is going to be these things. Now, how did we get those? We said for each sample where the model was wrong, and this is the one case where it was wrong, we keep the weight the same. Essentially, multiply it by beta raised to the 0, which is 1. So we multiply the weight by 1, and we have the same weight from round 1 into round 2 for the mistakes. Now, every one that we got correct, that's these 3, we, instead of multiplying it by 1, we multiply it by beta r raised to the first, which is beta r, which in this case is 0.33. So this is 0.08 is about 0.25 times 0.33, a little bit of rounding involved. And there are the weights that you're going to take out of this loop and into the next round. So let me clean up a little bit of these markings here. The next thing to do is, renormalize the weights. So we're going to take the weights that we have and normalize them so that they sum up to 1. And that is what that looks like. A little bit of multiplication, summations, etc., etc. Okay, the next thing we're doing is going to learn another hypothesis, H2, and let's see how H2 does. Okay, look at that. H2 did better at this example that H1 got wrong, and it got that right. But in exchange, while it was off chasing whatever that was, it started to make a new mistake that H1 didn't make. And that's okay, because H2 is focusing on a different part of the problem. It's not that each successive model suddenly gets more power on its own right. Each successive model is going to make mistakes, but hopefully there'll be different mistakes than the previous model made. And in essence, we'll be adding variance so that later when we give everybody a vote, those variance errors cancel each other out and we have a better overall model because each hypothesis has learned a different part of the concept. But okay, fine. Now we have to calculate the error of model 2. Now this is related to the P's, the sample weights. So this is how much of the mass did we get wrong. And so we got this guy wrong is the only thing wrong. So the sample mass we got wrong comes from right there. Boop. There you go. Calculate the beta the same way, a little bit of math. And now we reweight these again. Let me clear off a little bit here so that we can see this a little bit better. And remember, the samples that we got incorrect are going to keep their same weight. So this guy's weight gets promoted from the previous round, and every sample that we got correct is going to have its weight multiplied by beta. So it's going to get smaller. And so that's what we have. That's that times beta. That's that times beta. That's that times beta. And then when all of that's done, you go back around and renormalize. And you can see that the third version of the model, and this is where we're going to stop this little exercise, but the third version of the model would be chasing these two samples because this one was wrong on the first go round. This one was wrong on the second go round. These two samples at the top and the bottom, their weight has got quite a bit down weighted. It used to be 0.25 at the beginning. Now it's 0.01. Substantially less attention is being paid to those samples that every model up until this point has got right. And then at runtime, when you want to figure out the class of a new sample, you'd have x new. It's 1 if this summation is greater than 0.5, because remember, we're just doing binary classification. So this argmax thing, which is behind my back right here, this argmax, now I'll draw it again. This argmax thing here basically reduces into is it above the 0.5 threshold? And we'll say beta 1 is the vote that we associate with hypothesis 1. So log of 1 over beta 1. Remember, that vote is larger the closer you get to a very accurate model, and it's smaller as you get to an inaccurate model. So in this case, it would be something around there. And then you would add in the vote of hypothesis 2 using beta 2, which in that case is a little bit smaller. So that second model gets a little bit bigger vote than the first model got. And that's how you would calculate the class label, by using this ensemble that you learned through boosting. Now, that's the algorithm. You're going to have to go code it. You're going to have to take your decision trees. You're going to have to put in those really nice numeric attribute splitting points so that decision trees will work well on the adult census data set in the first place. Then you're going to need to add sample weighting into your decision trees. And then you're going to have to build that boosting algorithm we talked about. Then you're going to have to stitch them all together. Then you're going to have to do model tuning. Then you're going to have to write up your assignment. Then you're going to have to turn it in. And then the TA is going to have to grade it. Man, the amount of work involved in a machine learning course boggles the mind. But before all of that, let me give you a little summary. Boosting is an ensemble technique where each base model learns a part of the concept. And boosting can allow weak learners, or ones that have very high bias for the concept in question, to learn very complicated concepts quite well by forcing each model to learn the part of the concept that the previous models couldn't get at. So you kind of, at the limit, your very simple, weakish learner is learning just a tiny bit of the concept, and that's all it really needs to do. And it's okay if it gets everything else wrong. Those are all sample weighted way down because other people have already gotten them right. Boosting can help with both bias and variance type issues, but it can overfit, so you need to control the search by using a holdout set, stopping when you clearly are starting to see overfitting according to that holdout set. And a form of boosting called gradient boosting machines is widely used in practice. I've heard about it last week. I even heard about variance beyond this. I mean, people are actively working on algorithms in this boosted trees space. They're getting better and better all the time. Something you should learn more about, something you should add to your toolkit. All right, well, I hope you enjoyed this lecture. Part 2 of 3. Tune in pretty soon. I'll give you another lecture, part 3. See ya.